Hey everyone, this is Dr. Walker. This is video 552 combination of resistors. This video is going to be very similar to the video on capacitors where we simplified circuits and worked backwards. So the first thing is I want to remind you how to simplify circuits if you have resistors instead of capacitors. First thing is to draw each resistor and then find two or more resistors that are either in series or in parallel. Once you find them, you redraw the circuit, but you draw one equivalent resistor for the resistors that you're simplifying. And then you repeat. Now in your new circuit, you find two or more resistors in series or parallel, redraw the circuit, and draw the equivalent resistance. You're going to repeat this until you have one equivalent resistor for the circuit. So let's look at your turn just to remember this process and to help identify resistors in series and parallel. So which resistors would you simplify first? Go ahead and pause the video to think about it. So we have four resistors here, and we want to figure out which ones are either in series or in parallel. And I just want to go through all the different cases so that you can learn why they are or are not in series or parallel. For instance, if you think that R2 and R4 might be in series, well then I would say there's a junction here, so they're not in series. When you're in series, you can just have one connection between the two resistors, no junction. Junction is a point where the wires intersect. Okay, what if you thought R3 and R4 were in series? Well, it would be the same thing. They're not in series because there's a junction between. What if you thought R1 and R2 were in parallel? Well, even though they kind of look in parallel because they're across from each other, to be in parallel, there would have to be a junction on either side where they're connected. So if the left end of the resistor is connected to the right end, there would have to be a junction somewhere in there, like this, and there couldn't be anything else in the way like a battery. Likewise here, the R3 is in the way. It would just have to be a plain wire here, nothing else in the way. So definitely not in parallel. So where does that leave us? It leaves us with R3 and R4. Are these in series or in parallel? They may look in series, but they're actually in parallel. Whenever you have a resistor, you can redraw it along the same wire as long as you don't make it go through a junction. So R4, if you want, you could redraw it right here instead of right here. And then it's easier to see that they are in parallel. You can see that you have this end here connected to the top end with a junction in between, and likewise for the bottom end of the resistor and the bottom end of resistor 3, there's a junction in between. So you can move a resistor around as long as you're not moving it through a junction. You couldn't, for instance, move R3 over here, right? You couldn't put it over here because then you'd be moving it through this junction. Okay, so that was this question, but just for fun, we can go ahead and think about what would be the next step, right? So once we find two resistors in parallel, then we redraw the circuit, we simplify those two, and we draw one equivalent resistor for those two, which we'd call R34. And we leave the other two resistors as is. And it's even helpful to just draw a little line and remind yourself that those two were in parallel to get that one. And then you would go through the process again, find two or more resistors in series and parallel. Although before you do that, I would, right here underneath the new circuit, I would write down what the new resistance is. So when you're in parallel, we use the 1 over equation. So I would go ahead and calculate that equivalent resistance underneath the new circuit just to keep the work nice and organized. And then once you do that, then you have 3 resistors here, and hopefully you can see that they are in series because there's just one single connection between R1 and R34. There's also one single connection between R2 and R34. So they're all in series. They can all be simplified at the same time to one equivalent resistor. And then you could remind yourself that they were in series, and then you could use the addition equation to go ahead and find that new equivalent resistance, you just add all of the resistors together. So that was a quick reminder, maybe not so quick, but a reminder of how to simplify circuits. And then the next thing is working backwards with resistor circuits. So the takeaway message is that if you're in parallel, you bring back the voltage. If you're in series, you bring back the current. So here is the circuit that we were just looking at, and we just saw that it simplified to this R equivalent. We had these were in parallel, and we had these were in series. So without using numbers or solving through everything, what you would do, depending on what variable that you're looking for, let's say that you want to know, for instance, the current through R3, right? Let's say you want to know the current through R3, which I call I3. You would see that for this equivalent resistance, the three resistors were in series. When you're in series, you bring back the current. So that means that whatever current that you calculate for the equivalent resistor using Ohm's law, you're going to bring it back, and that current is going to be flowing through all three of these resistors. That means it's also flowing through R34. So you bring back the current because we were in series. Current is the same when you're in series. Once you have calculated once you have brought back the current for R34, now you look back at the previous step and you saw that R3 and R4 were in parallel. When we're in parallel, we bring back the voltage. So that means we have to calculate the voltage across R34 by using Ohm's law again. And once we do, put that over here so it's not in the way. Once we calculate the voltage here, then we bring back the voltage because we were in parallel. So that's the idea, is that you keep bringing back current or voltage until you can calculate the variable that you want. In the guided examples video, we will go over an example and use numbers and go through the whole process.